Hello, my name is Varun Kapoor and I am going to present a demo of VollSeg Napari plugin which I created to do segmentation of cells and tissues in 2D and 3D coming from different imaging modalities. And what you can see here is that VollSeg consists of different model type combinations that you can use to optimize the segmentation for your particular dataset. And in this demo, I'm going to show you examples of several datasets and the optimized settings to get the best segmentation results for them. My first dataset is that of Ascadian embryos. This dataset was imaged using light sheet microscope and it was imaged from 4 different angles, and then the images were fused together to get the image that you're seeing over here. I trained a UNet model in 3D for doing segmentation of these cells, and to actually do the segmentation of these cells, you can turn off the options of no denoising, no SARIS model, but using a pre-trained UNet model. And then the pre-trained UNet models are available, and all the pre-trained models are available on Zenodo, and if they have not been downloaded on your computer, it will automatically download it in the background. And then you can select the model type for the particular dataset. In this case, it's the embryo cell 3D model. Then you can see in this down panel, you have several choices to make. For example, what is the appropriate number of tiles that you can choose for running this computation on your GPU, or what are the display options that you want to see. For example, here I can say I just want to see my UNet results. And once you're happy with the selection, you click run. The process runs in the background, and then you just wait for the computations to be over, and it will show you this label image of the segmented cells on the left hand side over here. Once the computation has been done, you will see the results of the segmentation overlaid on top of the input image as over here. And to verify the results of the segmentation visually, you can just display them on the side and see how well the segmentation model performed on this example dataset. And this example dataset you can actually get from the open sample menu, where in VollSeg Napari embryo cell 3D is actually exactly this dataset. And then you can use this model as a pre-trained model to apply the segmentation on this dataset to get exactly the same results that you're seeing over here. And now let's try another example dataset. So if you go to the sample menu and do VollSeg Napari and open the breast cancer cell dataset, this is actually a dataset of human breast carcinoma cells, and they are coming from confocal microscopy. They were imaged in low signal to noise ratio condition, and for such kind of datasets, it is actually very common to have 8-bit or 12-bit images. So for this particular dataset, I found that an optimal combination is to combine StarS model with a denoising model, where the denoising model denoises the image and then it creates a semantic segmentation map from the denoised image. It uses the StarS model to get the seeds or the locations of where these cells are, and using the seed pooling approach of VollSeg, it does a marker controlled watershed on the probability map of StarS to give you instant segmentation of these irregularly shaped cells. So this model is also pre-trained. So if you go on 3D, you will see the carcinoma cells model will appear in the drop-down menu. No UNet model for this one, but a denoising model. So you will see in the menu is the denoising carcinoma. Again, you select your tiles which you think are appropriate for your GPU. And now here is the thing. Let's say you make a wrong choice of parameters and you hit run, and your process in the background is going out of memory all the time, and you are getting stuck in getting your results because it's never ending. So for this particular case, I made a stop time-lapse calculation button where it interrupts the running calculation by letting it run for the first time, for the time point that it is actually running on, because the calculation is running in the background thread and it's yielding these numbers which you are seeing in the progress bar over here. And when the new value gets yielded, it will also pass on the information to the worker, the thread worker, that actually the kill process was invoked, or the stop time-lapse calculation button was pressed. So the calculation has to stop. And when the calculation actually stops, this button will go back again from being red to being gray. And then you can change the parameters again and relaunch the calculation, rather than actually having to force quit Napari to start the calculation all over again. So now you can see that this actually went to the second time point, but then it yielded the value that the process has to be killed. So the process was killed and the button again became gray. So now you can actually reselect your parameter setting to, let's say, 8 styles, and let's start the running again, and it will start the whole process from the very first time point. And since the process is running in the background, you can reselect your display options and say that well, I just want to see all of them. So you restore the display defaults, and then you wait for the competition to be over. The progress bar will actually show you at which time point it is at that moment, and then you just wait it to go to 100% till you see all these results again appearing on the left hand side. And now in this case, you are not just going to see this instant segmentation map coming out of VollSeg. You will see the instant segmentation map of Stardust. You will see the binary segmentation map, which has been labeled, and you will see the denoised image and the probability map that we use for doing this watershed process on. And then you can choose to save whichever layer you want to save. And when the results are done, then you see all of these displays at once at the same time. So maybe you don't want this. So let's just take a look at some of these results and one by one. So this is the segmentation that you get out of VollSeg. These are the segmentation of the irregularly shaped cells, and you can see the kind of job it does in this 3D view of Napari. Yeah, and now we can compare it with the results that you get from Stardust, which approximates these cells using the star convex approximation. So this is like approximation of the shape that you would get from Stardust if you use this model and just look at the Stardust results. And these are the results that you will get if you are using the VollSeg setting of doing the marker control watershed for getting the segmentation of these cells. So, and of course you can always toggle these colors if it's not really visible in this particular color setting. Then you can also look at the binary results, which are the labels. So for example, if you are interested in these kind of structures, these filament-like fibroblasts, then you could actually just use the VollSeg binary results, because usually these fibroblast structures, they don't really overlap with each other. So depending upon what your interest is, you can actually save that particular result, and here you can see the effect of denoising on the image, and that is the base watershed image that was used for doing this marker controlled watershed on. So now once this example is done, now I will go over to another interesting case of using VollSeg for the case of nuclei segmentation in 3D. So now let's continue with another interesting case. So these are the cells in 3D of xenopus tissue, yeah. And the thing about these cells is that during the early stages they hardly can grow. It's also confocal, so 8-bit imaging, and there's a lot of zeros which are present in the background. And since there are a lot of zeros which are present in the background, it may cause issues in normalization of these images, which is a kind of important step when you're applying these kind of deep learning models. So this is the issue that I had when I was training a Stardust model on kind of patches coming from these cells, but then when I was applying it on early time points, I wasn't getting good results. So let's first see what happens if I use my customized Stardust model, no denoising for this one, and try to get the results of segmentation for that. Yeah, so this is the customized denoising model. I'm just going to tile this again to fit in the memory, and then I hit run to get the results of Stardust from this particular model. And now once you're done, you see that the kind of results that you get for the segmentation of these cells, it looks like really bad segmentation for these cells, because it seems like there's hardly any kind of match between the cells and the segmentation that you get for these cells, and it's because of the normalization issue. Here, the cells were present only in a very small region, so the region of interest was like just around here, but a lot of black pixels were included in the normalization step, so that kind of spoils the segmentation of these early time points. So for this, I developed a combination of using the STARDIST model with a customized region of interest model. What the customized region of interest model does is it actually first finds this region of interest and creates a bounding box in 3D and only performs normalization in this volume, does the segmentation in this volume, and then returns the results to you using the same STARDIST model. So we can just see the results of if instead of doing this, let me just call this as another name, star only, and now I'm going to use my STARDIST model with the ROI model, and then let's see the different results that we get. Okay, and here starts coming the results. Okay, so now let me only go and see what STARDIST results are actually giving me. Yeah, so now you see just by actually having a region of interest where you are actually doing this segmentation, the results are much better than if I was just using star only without this region of interest, right? This was the results that I was getting if I was not doing this region of interest, and this is the result that I get if I use actually this region of interest. And yeah, it's just the data is too big, so this is the region of interest which you get from the region of interest model, and then the segmentation is performed in a bounding volume of this particular region, normalization, segmentation, and then you get the results which look more nicer. It's like this is too empty to actually see it in this view, but we can just you see it like this in the 2D sliced view. So the results are much nicer. You can actually change the opacity of STARDIST layer to see this, and also maybe increase this opacity so that we can see the results. Yeah, in much nice way. Alright, so you can see that now you have actually very nicely segmented these nuclei in 3D using the ROI model. And this is the result that you get from using this particular mode of combination of VollSeg setting. And now I guess we are through the demo part of VollSeg plugin. Now a bit more about the repository where you can find it. So you can find it from the Napari hub, and the VollSeg Napari holds its source code. And then you find a table here where I've put the example images, the description of where those images come from, the links to the training data, the trained models, and also I've put the ground truth images for testing these different models, and I put optimal combinations. For example, this was the first data set that I showed you, this was the second one, and then I moved over to show you the data set of this nuclei where I use the ROI model. And you can also use this to segment data sets like medical images of lungs or turf images of kymographs to actually get the segmentation of the kymograph. And then I also provide some metrics of how the results of VollSeg using this optimal combination setting compares to that of ground truth. So if you click over here, you will find the standard metrics of measuring precision, recall accuracy, F1 curves over intersection over union thresholds, and then you will also see the true positive, and false negative rates for these different models that I trained for VollSeg Napari setting. Yes, so I guess for the demo part, this is all I have for you, and I will leave some time for questions.